Okay, can you hear me now? Like this? Yeah. Okay, hello, I'm Borštnik, and I will be presenting specialized network topologies, especially focusing on one network topology which we have developed for one of our newest clusters at the National Institute of Chemistry in Slovenia. My two co-authors are Doctors Milan Hodošcek and Dušanka JaneŽic. In the past decade, clusters have been an exciting topic of research. This is especially true of Beowulf-type clusters of personal computers that were first developed at the NASA Center in Maryland. Clusters are very effective for numerically intensive applications that can be effectively parallelized. And for such applications, they are a viable alternative to traditional supercomputers, which are based on using many, many processors with a very fast interconnection network, usually a local bus, since the processors are located in one central box. However, the main advantage of clusters over supercomputers is their low cost and that they can be built from off-the-shelf components that can be found in most any computer store. The origins of clusters date to the era of workstations in the 80s, when researchers networked the workstations, usually with a dedicated network, and used such a cluster to perform parallel computations. In recent years, a few developments have truly enabled clusters to achieve great performance. One is that PC processors, such as the Pentium 4s and Athlons, have far surpassed the performance of processors that have been used in supercomputers. And the other, which I believe is much more important, is that cheap and fast networking has become available for personal computers. For a cluster to function, the individual PCs must be networked together to form the cluster. The main bottlenecks The network is usually the main bottleneck, and the goal is to reduce the latency as much as possible while keeping the bandwidth high. Usually, switches are used to interconnect the PCs into the cluster network. They're widely used, widely available, and they have a very nice property in that all the computers connected to the switch can see each other since they are on the same network segment. However, they have two drawbacks. One is that they tend to be expensive, and they're not very expandable. A switch has a limited number of ports, so once you exceed the number of computers in the cluster, you have to cascade the switches together, which usually greatly diminishes the performance available for the network. One way of avoiding switches is to connect the PCs using point-to-point links. For example, for Ethernet technology, you place one network card in each computer and connect them with a crosswire. This tends to be relatively cheap, even if using current fast gigabit Ethernet technology. The way in which the PCs are connected is determined by their topology. These range from a simple ring in which each processor or computer is connected to two of its neighbors, thus forming a ring. And the topology can range up to a full graph in which every computer is connected to every single other computer. This is not very scalable since the links become overwhelming even with a modest number of computers. The drawback with this is that since not all of the computers are connected pairwise, they still need to talk to each other, if nothing else for simple ping tests. And this can be done by adding routes, either static or dynamic, so that each pair can see each other, or by simply adding a cheap slow switch or even a hub. This should not affect the performance of the entire cluster because the application running on the cluster should be written with the topology of it in mind. And usually the application uses a lower level communication library such as the Message Passing Interface, MPI, or PVM, the Parallel Virtual Machine, to perform the communication between the nodes. And some of the implementations of these libraries can be tuned to a particular topology, for example, a hypercube or a ring. Another approach is to design the hardware topology based on the needs, on the communication needs of the software that will run on it. Now for a just brief description of the difference between a logical and physical topology. For example, you probably all know Conway's Game of Life. And there each cell needs the state of 8 of its neighbors. Well, that describes the logical topology. And for a physical topology, we could map this onto a two-dimensional grid. And we could even take a shortcut that each cell, which is mapped to a processor, would only need to communicate with 4 of its neighbors. Well, this physical arrangement of the links and processors describes the physical topology. And in general, the physical topology should be at least as well connected as the needs of the logical topology. For example, you can use a program that uses a ring logical topology on a hypercube, but just the opposite would not be very effective. You would lose lots of time in the communication routines. Now to introduce the concept of how we designed our topology based on a program that we run extensively on this cluster. CHARM is a program for the molecular dynamics simulation of macromolecules. Basically, this is an n-body simulator, and it loops over 2 steps. One is that for each atom, you calculate the forces that act on it. And then in the second step, you move the atom to a new position depending on the forces acting upon it. And for these 2 steps, CHARM primarily uses only 2 communication routines that are also programmed in its own MPI derivative library, CMPI. The 2 routines are the distributed vector global sum and the distributed vector global broadcast. Oops. I'll try to explain this. This is the only hard slide, but please bear with me as it's almost needed to understand how we designed our topology. The 2 operations, the global sum and global broadcast, are very similar, so I will only describe the sum. The distributed vector global sum, we add the vectors that are present on, for example, 4 processors. The resulting vector is a component-wise sum of the components. For example, the sum of the first component is the sum of these components found in the first row of each processor. And since it's a distributed sum, the resulting sum vector is left distributed among the processors. The beauty of this is that if the number of processors is a power of 2, for example, 2, 4, 8, and so on, there exists an algorithm that can perform this in the log base 2 of the number of processor steps. For example, for 4 processors, it's 2 steps. And this scales very well, obviously because of the logarithm. And it has another property that in each step, the amount of data transferred is halved. So in the first step, here we have 8 transfers. In the second step, we only have 4. And if we map the processors onto a hypercube in 2 dimensions, that's just a square, each step transfers data only in 1 dimension. For example, the first dimension for the first step and the second dimension for the second step. Now, if we keep this mapping of the processors onto a hypercube, we see that for each dimension in the hypercube, a different amount of data is transferred, as this picture here exemplifies. So we use these properties in designing the hierarchical hypercube topology. This is a physical topology of a hypercube in which the links are of different speeds. these are patterned on the two distributed vector global sum and broadcast operations, in that the first dimension of this hypercube is the fastest, the second is somewhat slower, and so on. And ideally, the speeds of the links would be matched to the amount of data transferred in the links of that dimension. So we use the hierarchical hypercube topology in the design of one of our clusters, the CRO 5. CRO stands for columns and rows of workstations. We use it to connect the 16 dual processor machines into a cluster. The 32 processors are Athlon MP1600. And here I will show the interconnections. These are the links between processors. These are the first dimension and the fastest. The transfer speed is greater than 2 gigabits per second. The second dimension, which not need be as fast, they are pairwise gigabit Ethernet connections between pairs of machines. There's 8 such connections. And the third, fourth, and fifth dimensions are simply mapped onto a fast Ethernet switch. If nothing else, you can imagine that this whole topology is faster than using just a fast Ethernet switch. And to test the comparison of this topology to others, in one case, we replace the switch with a gigabit Ethernet switch. So the slowest connection would be at a gigabit speed. And in the second case, we remove the gigabit point-to-point links so that all the computers were connected with the switch, but we left the local bus connection since it's a common property of clusters to use SMP dual processor machines. We ran a benchmark that is very network intensive, and also it explains why the results are generally low. In this table, we present the speed up. That is the how much faster the benchmark ran on a number of processors compared to only one processor. In general, bigger is better. As you can see, the hierarchical hypercube in the top row performed almost as well as using only a gigabit Ethernet switch. And it performed vastly better than using the fast Ethernet switch. Now keep in mind that the cost of the hierarchical hypercube only adds, the only additional cost is the pairwise Ethernet links. We could add more links for the remaining dimensions, but we discovered that the benefit is not too great. Another feature of using point-to-point links to connect clusters, not just computational clusters such as ours, but in general any cluster of computers, is the inherent redundancy of such a cluster. With appropriate dynamic routing, any link failure can be routed around, or even a switch failure. For this, each computer needs at least 2 connections, either with a point-to-point link to another computer or to a switch. And the topology can even be optimized toward the greatest possible redundancy given a limited number of links. So in conclusion, I'd like to state that clusters are very appropriate for numerically intensive applications. The appropriateness of the cluster depends on the application itself. And for the cluster, the type of networking is very, very important to its effect on the performance. An appropriate topology for a given application is detrimental in its effect on the performance of a cluster for that application. And we have developed a hierarchical hypercube topology that is based on the communication patterns of a program we run on the cluster, and it has shown significant speedups in the application performance on our cluster. And this topology offers a performance improvement over standard switching technology for only a small additional cost in the adding of the gigabit point-to-point links. And I would like to thank the Ministry of Education, Science and Sport of Slovenia for the financial support of this project. Thank you.
Okay. Any questions? I have a question. Which are the physical distances in which such kind of topologies, which are mainly local topologies, can really be useful, and which is the size over which you can't extend this physical hypercube topology?
Yes. For this topology, we used a copper gigabit Ethernet. So basically, that is the limiting distance between the boxes. We keep the cluster in one room for practical purposes, but it could be spread out around the desktops. Well, a common concern is the scaling of such architectures. For example, a hypercube, well, you can only fit so many network cards into one box. For example, the predecessor, the Crow 4 system, was a 64 PC cluster built with a hypercube, and we basically put 6 network cards in each PC, and we had no slots left for any other cards. But in general, the scalability is also dependent on the application. In that, for example, the benchmark did not scale very well. For 32 processors, the best speedup was 10, which is only 30% of the possible performance, let's say. And this is usually due to network losses, and just exemplifies how the network is very important to the performance of a cluster. And it is very dependent on the application.
Let's thank the speaker. Oh, yeah, please.
Question is, why are you using AMD processor instead of Intel?
Well, price was a major concern for this project, and we determined that for the floating point operations that are present in this application and some of the others that are run on this cluster, the Athlon just performed better for the given price.
It looks like, why Ethernet instead of ATM?
Yes. For example, we could have just used a gigabit switch, but that was costly at the time. We had one for the benchmarking later on, but when we designed it, it was not available to us.
Okay, let's thank the speakers again.